We are live. What is up, party people? Uh, what is up? What's up, party people? It's Mr. Harris, and I am back with another lesson. We are in Unit 6. Lesson 6. Do me a good favor. Like, share, and subscribe to the channel. Especially if you're my student. You never know. I might give you some extra points for subscribing. Hint, hint. This one is talking about exponential growth and how we represent exponential growth. So we are working in our workbook starting on page 56, I believe. If I share my screen, then you'll know where we are. Let's do this in presentation mode. And so here we go. We are on page 56, and you have this scenario. It talks about a food company currently has 5 convenience stores. It is considering 2 plans for expanding its chain of stores. The first plan, Plan A, is to open 20 new stores each year. And you want to use technology to complete the table for the number of stores for the next 10 years as shown. Now, in this chart, it only says 6 years, but you can, by the time you do the first 6, you'll know how to do the other 10. So if we are open 20 new stores each year, right? So we started out with 5 in year 0. Remember, that's the initial value whenever the X term is 0. All right, so after year 1, they would have 25 stores, right? And so the difference from the previous year would actually be 20. So how would I find the difference? I would find this year, which is 25 stores, minus last year, which is 5 stores, and I get a difference of 20. And so next year, they would add 20. Oh, Lord, that's not 42, it's 45. All right, and then from 45 minus 25, that equals 20 as well. And then we would have 65, which is another difference of 20. 85, another difference of 20. 105, another difference of 20. And 125 stores. And that is also a difference of 20. So notice you have a common difference in this case of 20 each year. So if it's increasing by 20 each year, we want to think about how is that changing. Remember, we've been talking about linear growth compared to exponential growth. Okay, so when we go to the next slide, let's look at some questions about this. And so the question says, what do you notice about the difference from year to year? Okay, so that common difference that we were talking about, the difference is 20. Okay, and it's the same each year. The common difference is 20, so we could say it's the same, and specifically it's the same being 20 stores each year. But then notice it says if there are N stores in 1 year, how many stores will there be in a year later? And so if there were N stores, let's say we start with N, and then notice we just add 20 to N, and that is that. Okay, so notice it's the same growth each year. So this is going to be linear growth because it's only adding the same amount each year. Okay, so that's linear growth. Let's go on to the next part of this. Remember, we're still talking about this store chain that starts with 5 stores, and it has 2 plans. Plan A was to increase by 20 stores each year. Plan B is to double the number of stores each year. So we want to see, well, how do we complete this table? All right, so if I start out with 5 stores, and in the initial year, year 0, if I double that, that is 10, right? So the difference from the previous year is going to be 5 in this case. And the factor from the previous year, I'm going to show you how we do this. We have, we could say 10 divided by 5 equals 2, or you can start with the initial one, 5 times what equals 10, okay? But I like to go from the current year and divide it by the previous year to find that factor. If I have 10 stores and I double that, that's going to give me 20 stores. right? So then that means the difference is 10. And then once again, if I say 20 divided by, so that's this year's stores of 20 divided by last year's stores of 10, I get 2. If that 20 doubles, then I get 40, right? And that is a difference of 20 stores. And then 40 divided by 20 equals 2. All right, so we go from 40 to 80, and that's a difference of 40. Still, the factor is 2. For 40 times 2 is 80, or 80 divided by 40 is 2. 80 doubled is 160, right? And now that difference is 80. It has a common factor from the previous year. 160 divided by 80 is 2. And then from 160, we double that to get 320. And now that difference is 160. Still a common factor of 2, okay? So as you can notice, every year, the current year's store, we're multiplying that by 2 each year, okay? And so we have a couple questions in regards to this situation, all right? So the question says, what do you notice about the difference from year to year, okay? And the difference from year to year, notice it doubles. Or okay, let's just say it doubles. Or let me see, it increases each year or doubles each year. Let's write it like that. All right. When we look at the next one, it says, what do you notice about the factor from year to year? It remains the same at 2. So the factor from year to year is we take this year's number of stores, we multiply it by 2. So remember, factors is numbers that you're multiplying, so it multiplies by 2. So if there are in stores 1 year, how many stores will there be the next year? 2 times that number of stores. So n is the number of stores, and then we want to know how many stores they're going to be next year, then we just multiply it by 2, or we show that by 2n. All right. This is a place where you can pause, stop, rewind, things like that. But we are going to go to activity 2. It says match each representation with situation 1 or situation 2. Be prepared to explain how the table or expression answers the question. Situation 1, a person has 80 followers on social media. The number of followers triples each year. How many followers will she have after 4 years? Situation 2 says, a tank contains 80 gallons of water and is getting filled at a rate of 3 gallons per minute. How many gallons of water will be in the tank after 4 minutes? Important information, okay? The number of followers triples each year. So it triples. When you triple something, you're multiplying by 3, okay? This one, so that's the initial value of 80 followers. Here we have an initial value of 80 gallons of water, and it's filled at a rate of 3 gallons per minute, okay? So now each situation A, B, C, D, we're going to see which one of these does it match, situation 1 or situation 2. Here, I start with 80, and then I multiply by 3, I multiply by 3, I multiply by 3. This is situation 1, okay? Situation 1. And let's put a 1 like that so y'all know it's a 1, all right? We have these X values in this table, 0, 1, 2, 3, 4. The Y values are 80. That's the initial value. 240, 720, 2,160, 6,480. Well, guess what? What's happening? If I actually multiply by 3 here, 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 and of course here, boom, then this looks like it models situation 1 as well. Because remember, situation 1, it says that the followers are tripling each and every year. Let's go forward. All right, so we're still matching these situations. Now I have 80 plus 3 plus 3 plus 3 plus 3. All right, that looks like a scenario for situation 2. And why is my computer not typing? Okay, here we go. Let's do situation 2. Made me think about that song. Situation number 9. All right, now this one D is 80 plus 4 times 3. All right, but if you look at this previous expression right here, notice that there are 4 threes. All right, so if I have 3 plus 3 plus 3 plus 3, there's 4 threes. So I can just say 4 times 3. So that's going to be situation number 2. All right, situation 2 for both of these. Let's move forward. Here in this one, we have, it says match each presentation, same thing, same directions. My bad. I don't know why. A, B, C, D, E, and F. Now, notice this one in Y, it is increasing by 3 each time. I start with 80 for my Y, then I go to 83, 86, 89. So I'm adding 3 each for each value of X. That's just like the tank. It says it's increasing, it's filled at a rate of 3 gallons per minute. Okay. And then now look at this one, F, 8 times 81. And you might say, I don't know where they got that 81 from. But guess what? That 81, if I actually am tripling the numbers each year, then boom, here, let's write this. All right, so I started, if we remember, A said 80 times 3 times 3 times 3 times 3. Well, guess what? This can be written and 3 times 3 times 3 times 3 is 81. So this is definitely going to be situation 1. And we're going to use this information to answer actually letter H as well. Okay. Next slide. G, 80 plus 12. Now remember in situation D, we had 80 plus 4 times 3. So 4 times 3, you already know is 12, homie. So we're going to say situation 2, all right? And then in situation H, we have 80 times 3 to the 4th power. Well, notice in A, we had 80 times 3 times 3 times 3 times 3. And in situation F, we had 80 times 81. Well, guess what? 3 to the 4th power is 81. So you can tell by that information that this goes with situation number 1. All right. Hopefully y'all are understanding this. If not, stop, pause. Oh, I forgot to shout out to people that just might be watching this thing live. If you're watching this live, put a 1 in the chat. If you're watching the replay too, put something in the chat. Holla at your boy. Tell me what city you watching from. If you're one of my students, shout out B215, whatever. You can shout out your class. Class of 2027. Whatever y'all want to do. But just let me know you're watching in the chat. I almost pressed the wrong button because I'm talking too much. And let's run that back. Let's stop this annotation. I knew I was supposed to be pressing something. And let's look at another activity. Activity 3. This one's going to be pretty quick. This one it says the diagram shows the number of cells. The diagram shows the number of bacteria in hour 0 and then in hour 1. Draw what happens in hours 2 and 3. I think the next slide is where we draw it at. Let's do it like this, okay? So here, let's go back. Draw what happens in hours 2 and 3. We could draw it here, but we're gonna have to draw the same thing in the next slide. So let's indeed go back to this next slide. All right. So look at this. Notice you have 1 bacteria cell that's split into 2 bacteria cells. So obviously the pattern is going to continue. So this one splits into 2, and then this one splits into 2. All right. And then each of these split into 2. 1, 2, 1, 2, 1, 2, and 1, 2. All right. So how many bacteria are there in hours 2 and 3? Now notice if I change this color, this would be hour 0, hour 1, hour 2, and hour 3, right? Now, we have to calculate all of the total number of cells. So in hour 1, we would have a total of, so let's do hour 0, we had 1 cell. Hour 1, we had 2 cells. Hour 2, if we count all these new ones, 1, 2, 3, 4, and then 5, 6, 7, because we have to count the ones that were there already. Hour 3, we count that 7, and then we add 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 cells in hour 3. There are 7 cells in hour 2. And we can continue this pattern on and on like Erykah Badu. All right. Let's go to the next one. Let's go to the next activity 4. Now, this one's a little detailed. This activity probably is the most important activity from this lesson, right? And so I'm going to do my best to go over this, right? So we start with, it says in a medical research lab, 500 HeLa cells double approximately every 24 hours or every day. In the middle column, the expression to show how to find the number of HeLa cells after each day has been started for you. Complete each expression in the middle column. All right, so notice I have 500 cells. These cells are going to double. All right, so they're going to multiply by 2, okay? So now I got 500, but let's say since it's the first hour, it's going to multiply by 2, but it's no time. And 2 to the 0 power is 1. Remember, anything to the 0 power is 1. Don't y'all forget it for my students, okay? So I basically have 500. 2 to the 0 power is 1, so 500 times 1 is 1. Okay, after the first hour, I have 2 to the 1 power. Okay, well, 2 to the 1 power is 2, so 500 times 2 is 1,000. Okay, here I have 2 times 2, okay, because it's 2 hours, so it doubles the first hour, then it doubles the second hour, right? So now I have 2 times 2 is 4, 500 times 4 is 2,000. Notice it's doubling. Same thing, 2 times 2 times 2. It's doubling the first hour, double the second hour, double the third hour. So that's the same thing as 500 times 8, because 2 to the third power is 8, which would give me 4,000. All right. Notice here, our X value goes down to 6. Our day goes to 6. We skipped 4 or 5. All right. So now those are exponents. So it's times 2, and it's going to double 6 times. So it's times 2 to the 6th power, which now goes up to 32,000, I believe. Okay. 32,000. Let me double check. Let me do my math. Where's my handy dandy calculator? Y'all hold on a minute. Hold on. All right. And I just double check my math. Listen, the calculator is the tool. I got 500, and then I say 2 to the 6th power, multiplied it by, 32,000. I knew my math was mathing, homie. All right. And then so now here, if we have the day T, well, it's doubling T times. Okay. So I have 500 times 2 to the T power. All right. So that's the pattern. This is exponential growth. It's doubling, but remember, when you go from day 3 to day 6, that 4,000 to 32,000 is not doubling because the number of days, it's doubled 3 times since that 4,000. So go from 4,000 to 8,000, 8,000 to 16,000, 16,000 to 32,000. Whew. Let's go on. Change. Okay, we already did this part. So it says write an equation relating in the number of cells to T, the number of days. All right. And so we just simply write what we just wrote in the table, but we're going to say N equals because it says relating in. So N equals 500 times 2 to the T power. Okay. Notice I could also write it as in function notation as N of T equals 500 times 2 to the T power. Okay. Use your equation to find N when t is equal to 0. What does this value of n mean in this situation? So if I'm going to write it in function notation, t equals 0, 500 times 2 to the 0 power. Remember, any number to the 0 power is 1. So 2 to the 0 power is 1. So n of 0 is 500 times 1, which equals 500, okay? So what that's saying is when the time is 0, there are 500 HeLa cells. Well, they told us in the first slide of activity 4 that, or actually it shows it right up here. All right, in a medical research lab, 500 HeLa cells, I've been saying TeLa cells, I think. HeLa cells double approximately every 24 hours. This represents the initial value, okay? The initial value. So when that input, the X value or whatever variable they use, but whenever that input is 0, that's going to be the initial value, all right? Now, I don't know if I actually put activity 5 up here. I might have, I might not have. And we got another question on activity 4. So notice it says, in a different medical research lab, a population of single cell parasites also reproduces. Equation which gives the number of parasites P after T days is P equals 100 times 3 to the T power. Explain what the numbers 100 and 3 mean, okay? So 100, notice that initial value is always that first number. 300 represents the initial population of parasites, okay? And we're going to put in parentheses initial value, okay? The 3 represents the multiplier, multiplier, okay? And we're going to put triple in parentheses, okay? So that 3 is talking about the fact that this population is tripling every hour. It doesn't say how many or what. It doesn't say at what rate. It just says T. So we're going to assume that it's like the other one where it's tripling every 24 hours, okay? So these are very, very important things in regards to exponential growth. The initial value is always that first number, right? Or where you begin, okay? And then, you know what? Hold up, wait, I put 300 on here. Look, see, sometimes you keep talking and it's important. All right, so that 100, represents the initial population of parasites, and 3 represents the multiplier, meaning that it triples, okay? Now, I don't know if I put activity 5 up here. If I did, I'm going to do it. If I didn't, I didn't. Okay. I don't want to really go over these real quick. We could talk about them, but I'm going to skip that part. We did put this up here. All right, so let's go over this real quick. Activity 5. Looks like this video going to be kind of long, y'all, but it's all good. All right, so here, we had a table previously, and so we want to graph T and N when T is equal to 0, 1, 2, 3, and 4. Okay, so now this is talking about the initial population from activity 4, where we had 500 TeLa cells. All right, so boom. Now let's label our x-axis real quick. All right, so 1, 2, 3, 2, 3, 4, and then this would be 5. All right, so, and this would be our days. Okay, we could do increments of 24 representing hours. So it will be 24, 48, 72, 96, something like that. I'm not sure. But in this case, we're just doing days. All right. So the initial value, it starts out with 500. After day 1, it doubles. All right. So after day 1, it's 1,000. All right. So boom here. And then if that doubles after day 2, it's going to be 2,000. And if that doubles after day 3, it's going to be 4,000. And if that doubles, it's going to be 8,000. And then if 8,000 doubles, we can't see it, okay? So that would be the graph for t equaling 1, 2, 3, and 4. And the number of cells, so we could label this number of cells. I keep saying telecells, it's helicells. All right. So that's that. That's what the graph looks like. Okay. Now let's look at the second one. So this is the one where it starts out with 500 and it doubles every hour. We're going to look at the next one where refer back to your work in the table of the previous task. Use the information given to quarter planes for following graph T and P. Okay. So T and P, remember, this scenario in number 2 says P is equal to 100 times 3 to the T power. So P is equal to 100. It triples every hour to the third power. Okay, so 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4, and then we don't need the 5. All right. So this is days. I keep saying hours. I apologize. Not a big difference in this case, but it would matter in some cases. Okay, so we start out with 100. So we're gonna be way down here. Okay, because if this is 1,000, then that means this is 500. So that means that's 250. So 100. And then if that 100 triples, 100 times 3 is 900. So it's going to be up there. And 900 times 3 is 2,700. So it's going to be about right here. And then 27 times 3 is going to be about 50. Wait, hold up. Let me make sure my math. Okay, so we started out at 100. Oh, I skipped one. I'm sorry, y'all. I knew something was looking weird. Let's go back. All right, so we started out with 100 and we tripled. So that's 300. Okay, so that's about right here. I'm sorry. And then 300 goes to 900, so that's about right here. And 900 goes to 2,700, which is about right here. 2,700 times 3 is 8,100. So after hour 4, day 4, we're up here. We're like 8,100. So let's go right here. Okay. So notice this is exponential growth. Remember, it starts off small. 100 triples to go to 300. 300 triples to go to 900. 900 triples to go to 2,700. And 2,700 triples to go to 8,100. All right. So that's what this graph would look like. All right. You may have to stop and look at this again. Remember, mistakes are your friend. That means you're doing some work or something like that. So I don't mind telling y'all my mistakes. All right. So when we graph these, notice the first one we're graphing the equation n equals 500 times 2 to the t power. The second one we're graphing p equals 100 times 3 to the t power. Okay. So now we don't have to do this part because you all are not in the classroom. That's for my classroom. And that is that. Now I can stop sharing. Thank you for watching this. Remember, like, share, and subscribe. Pause, rewind. I know this one's kind of long, so you can skip through it. If I have time, I actually go through and type in the minutes for each activity so you can have a timestamp. Thank you so much for watching. Remember, I got the solution to your